One of the features of our Larson-Farber textbook is the try-it-yourself problem. These typically occur after an example. The example models what you're supposed to do. I am going to work out the try-it-yourself problems in section 8.2. These are two sample t-tests for differences between means, and in particular the first try-it-yourself problem, which is on page 430, is a comparison of the earnings between high school diploma earning students and associate degree earning students. Let me read it. The annual earnings of 25 people with a high school diploma and 16 people with an associate's degree are illustrated in this table. Can you conclude that there is a difference in the mean annual earnings based on level of education? Use alpha equals 0.05. Assume the populations are normally distributed and the population variances are not equal. Well, if you look at our sample standard deviations, that would be enough to indicate that you wouldn't expect the variances for these populations to be the same. These look quite different. Let's figure out what the claims are and what the hypotheses are. Basically, we just want to know if there's a difference. So the null hypothesis would be that there isn't one, that you have equality. Remember that equality always has to be in your null hypothesis. The alternative would be that they're not equal, which, by the way, is the claim. All right. Now let's figure out what's going to happen. If you looked at the first set of data, df would be n1 minus 1, which is 25 minus 1, so it looks like 24 degrees of freedom. But if you look at the other case, the associate's degree, n2 minus 1, 16 minus 1 equals 15, 15 degrees of freedom. And the rule when you're doing this sort of thing is you go with the more restrictive of the two. So 15 degrees of freedom is what we're looking at. If we go to our calculator and check out inverse t, we've got 0.05. So it's going to be 2.5% in a two-tailed test because of this situation here. Not equal can be less than or greater than. So I'm taking 0.025, 15 degrees of freedom, and thanks to the calculator, minus 2.131. Okay? So my critical t value is 2.131. If I were looking at a t distribution and looking at 0.25, looking at 0.25 at either end, I'd have 2.131 on one side and minus 2.131 on the other. If we get a statistic that falls in either outlying region above or below, then we would reject the null hypothesis and we would assume there is a difference. Let's find out what our statistic is. Hold on, this is a messy calculation, so be careful. The statistic, t-value statistic, 15 degrees of freedom, we have the difference of the sample means minus the difference of the assumed means for the population, okay? And because the variances are assumed difference, in other words, we don't expect the standard deviations to come out the same, the formula has sample variance 1 over n1 plus sample variance 2 over n2. So let's plug all of this in. Here we have 3, 6, 8, 7, 5, minus 44900 minus, well, according to the null hypothesis, these are the same, so that's just a big fat 0. And then down here, in the square root, we're supposed to take 5475 and square it and divide it by 25. And we take 8580 and square it and divide it by 16. Feed that into your calculator a few times until you agree on what the result is supposed to be, and you get about minus 3.33, rounding to only 2 places. Well, where are we? We're way down here. We're deep inside that rejection region. So, in other words, in this case, we can reject the null hypothesis, and that provides support for the claim. It supports the claim that there is a difference. So that's the first try-it-yourself problem. On the facing page, 431, we have a different setup. And in this instance, we're looking at a claim by a manufacturer who says the mean driving cost per mile of his minivans is less than the cost per mile of its leading competitor. So here's the manufacturer and his claim that on the average it costs 52 cents per mile to operate one of his minivans. We have a standard deviation, sample standard deviation of 8 cents per mile, and the sample size is 34. The competitor, the data for the competitor says, 54 cents per mile, so it's a little more expensive. The standard deviation is 7 cents per mile, and the sample size is 38, and we're doing this at the 10% level of significance. So what are we going to do in this case? Well, in this instance, we're going to assume that we have a situation where the variances are the same. Okay, that's the setup for this one. And we look at these results, and they're pretty close, all right? They're pretty close, so we're going to assume that the population variances are in fact equal, and we're going to do a computation on that basis. As before, we will look at the situation for degrees of freedom, and I think you can see that this one is going to give us 33, and this one is going to give us 37. But when you have equal variances, you have to pull out the special degrees of freedom formula, okay? And that formula is this. You take N1, you add N2, and then you subtract 2 from them, okay? So in other words, you're going to take the 33 from here and the 38 from here, and the 37 from here and add them. 34 plus 38 minus 2, okay? And when you compute this, looks like you have 70 degrees of freedom. It's an awfully big number for degrees of freedom, okay? And if you check it out, let's see what our hypothesis is. The null hypothesis, okay? The manufacturer is claiming that his costs are less, okay? So that's the claim. It's a strict inequality, so it has to be over here. The claim that mu1 is less than mu2, okay? So that's the claim, which leaves the equality in the null hypothesis. Well, I guess mu1 is greater than or equal to mu2. All right? If you check for the rejection region, remember, this is one-sided. It's a one-tail test. Because the null hypothesis says that mu1 is above here, okay, to the right, our rejection region is 10% down below. Okay, it's one-sided. And you're going to find out when you check this that your critical value is minus 1.294. Okay? And we know how to find that. Let's find out what our statistic is. I kind of apologize for this computation because this is even worse than the previous one. So check out what happens. The statistic starts off the same as before. You take x1, you subtract x2. Difference in means. And then you subtract the difference in the population means. So far, so good. Because you're assuming that the variances are equal between the two populations, you do a pooled variance here, and, well, let me just do it. Fortunately, we didn't have to derive this formula, we just use it. You take n1 minus 1 s1 squared plus n2 minus 1 s2 squared, add those together, divide by that combined degrees of freedom, and, just for fun, we have this extra factor. And you should be grateful right now that we didn't have to derive this. Okay, there's the formula. And if you start plugging into things, let's see what happens. You've got 52 cents minus 54 cents. The null hypothesis assumes equality, 0. That's nice. I have a couple of square roots to compute here. So let's see, it's going to be 33 times 8 cents squared. And you're going to add 37 times 7 cents squared. And you're going to divide the whole thing by the improved degrees of freedom. And as you will recall, that was 70. And then we have this extra business over here, 1 over 34 plus 1 over 38, all inside the square root. And once again, this can be a bit of a challenge to compute, but after you crunch it all out, you will get minus 1.13. Okay? And minus 1.13 is not quite there. Okay? It's not far enough into the negative region to hit the rejection area. So in other words, in this case, fail to reject the null hypothesis. And because we fail to reject the null hypothesis, we are not finding support for the manufacturer's claim. And that takes care of two good examples direct from the textbook of the try it yourself problems, and I hope you find that helpful.